Yellowstone just cracked open again, and this time, scientists caught it on camera. At 5:09 in the morning on June 13th, 2026, monitoring equipment buried in the ground at Biscuit Basin picked up something unusual. A burst of seismic energy, a low-frequency acoustic pulse rolling through the Earth. Within hours, the Firehole River, normally crystal clear, had turned milky gray for more than 3 miles downstream. Steam and debris shot into the air near a thermal feature called Black Diamond Pool, carving 3 brand new vents into the ground and blasting rocks several feet into the sky. It wasn't the first time this exact spot had done this. It wouldn't be the last. And for the scientists who spend their careers watching the ground beneath Yellowstone breathe, shift, and occasionally rupture, this single event was just one thread in a much larger story that has been quietly unfolding underground for the better part of 2 years. A story that is now forcing researchers to rethink what they thought they understood about the most famous supervolcano on Earth. To understand why this moment matters, you have to understand what Yellowstone actually is. Most people picture a mountain with a crater, the kind of volcano that erupts in a single dramatic cone-shaped explosion. Yellowstone isn't that. It's a caldera, a vast, collapsed basin roughly 30 by 45 miles wide, sitting in the northwest corner of Wyoming and spilling into Montana and Idaho. The basin formed not from a mountain building up, but from the ground caving in after enormous volumes of magma erupted and drained the chamber that had been holding it up. This has happened at least twice in the last 2.1 million years, releasing more than 1,000 cubic kilometers of magma, ash, and rock each time. Eruptions so large that geologists classify them as super eruptions, a category reserved for events capable of altering climate and ecosystems across entire continents. The most recent of these caldera-forming eruptions occurred around 631,000 years ago, leaving behind the Lava Creek Tuff, a layer of volcanic rock that geologists still study today to reconstruct exactly what happened. Since then, Yellowstone has not gone quiet. It has simply changed how it expresses itself. Instead of another catastrophic eruption, the region has spent hundreds of thousands of years venting heat and pressure through the extraordinary hydrothermal system that now defines the park. More geysers, hot springs, mud pots, and fumaroles than anywhere else on the planet. Old Faithful, Grand Prismatic Spring, the Norris Geyser Basin, these are not separate attractions. They are the visible plumbing of a single underground system fed by water that seeps down through cracks in the crust, gets superheated by the magma below, and forces its way back to the surface. This constant circulation is, in a very real sense, how Yellowstone breathes. And breathing, as any geologist will tell you, is very different from an eruption. It is a release valve, not a buildup. For decades, the primary way scientists tracked this system was through ground deformation and earthquake counts. Every month, the University of Utah Seismograph Stations, which operates the Yellowstone Seismic Network on behalf of the Yellowstone Volcano Observatory, tallies up the earthquakes recorded across the region. Most months look almost identical to each other. In April 2026, for instance, the network located 97 earthquakes across the Yellowstone region, with the largest a modest magnitude 2. 5 micro-earthquake south-southeast of Mammoth Hot Springs. Within that total sat a swarm of 16 small quakes over just 2 days in mid-April. To someone unfamiliar with Yellowstone, a swarm of earthquakes might sound alarming. To the scientists who monitor it, this is Tuesday. Swarms are a defining feature of life inside this caldera. They reflect fluids moving through fractured rock, stress redistributing along fault lines, and the constant micro-adjustments of a landscape that never truly sits still. But starting in July 2025, something slightly different began. A section of ground on the north rim of the Yellowstone caldera started to rise. This wasn't unprecedented. The exact same area had lifted in 1996 and again in 2004, an event scientists had already named the Norris Uplift Anomaly. That earlier uplift had researchers asking hard questions at the time. Could this kind of localized swelling lead to larger earthquakes, or to a dangerous buildup of hydrothermal fluid just beneath the surface, primed to erupt violently if the pressure found a weak point? Those questions never fully resolved, which is part of why the return of uplift in the same spot in 2025 caught scientific attention. For roughly 6 months, GPS stations recorded the ground steadily creeping upward. Then, by mid-January 2026, it stopped. USGS deformation data has shown no significant uplift or subsidence of the caldera since. As of the most recent monthly reports, earthquake activity across Yellowstone sits at background levels, and continuous GPS stations show little net movement in the region. The swelling that had scientists watching closely simply settled back down, the way it has before, without triggering the kind of runaway process that would signal genuine danger. That would seem to close the story, except it didn't, because while the ground itself went quiet, the science happening around Yellowstone entered one of the most active periods in its history. In the span of about 12 months, 3 separate lines of research converged to fundamentally change how scientists understand what's actually happening beneath the park. And it's this convergence, more than any single tremor or uplift that represents the real shift people are now calling a new phase. The first piece came from an unexpected direction: artificial intelligence applied to old data. A team led by engineering professor Bing Li at Western University, working alongside researchers from the Universidad Industrial de Santander in Colombia and the U.S. Geological Survey, took 15 years of previously recorded seismic waveforms from Yellowstone, covering 2008 through 2022, and ran them through machine learning algorithms designed to detect faint earthquake signals that human analysts and traditional detection software had missed. The results, published in the journal Science Advances, were striking. The team identified more than 86,000 earthquakes in that 15-year window, roughly 10 times the number that had been cataloged using conventional methods. USGS seismologist David Shelley, one of the researchers involved, explained that applying these techniques across a much larger span of time and space allowed the team to detect events that simply hadn't registered before, while also pinning down far more precise locations for quakes that had been recorded but poorly mapped. What the newly revealed data showed was not a story of a system quietly building toward catastrophe. It showed something more intricate. More than half of these 86,000 events belong to earthquake swarms, clusters of small interconnected quakes that occur in a confined area over a short period of time, distinct from aftershocks that trail a single larger main shock. These swarms clustered along young, rough fault lines rather than the older, smoother faults researchers might have expected, and researchers believe most of this activity is triggered by fluid, water moving deep underground, sometimes surging through a fault system for a while, then going still in that same spot for years, only to reactivate later. It's a picture of Yellowstone as a restless, fluid-driven system in constant low-level motion, not one steadily approaching a tipping point. As the researchers themselves noted, uncovering this activity is not a cause for panic. It's a cause for better science. Knowing exactly how, where, and why these swarms happen gives the Yellowstone Volcano Observatory a sharper baseline against which any future, genuinely abnormal signal could be measured and understood. The second major development answered a question that had puzzled volcanologists for years. If Yellowstone sits atop such an enormous, long-lived reservoir of molten and partially molten rock, why hasn't the pressure inside it built to the point of triggering another catastrophic eruption? In 2025, a team of researchers from Rice University, the University of New Mexico, the University of Utah, and the University of Texas at Dallas set out to answer that question directly, publishing their findings in the journal Nature. Using a 53,000-pound vibro-sized truck to send controlled vibrations into the ground and recording the echoes with more than 600 seismic sensors spread across the region, the team produced one of the clearest images ever captured of what lies just beneath Yellowstone's northeastern caldera. What they found was a sharp, gas-rich cap sitting about 3.8 kilometers, or roughly 2.4 miles below the surface, the literal boundary where Yellowstone's magma reservoir begins. This cap is an unusual mixture, partly molten rock threaded through with bubbles of supercritical water, a state of matter that exists under extreme heat and pressure. Crucially, the cap is only slightly porous, and that detail changes everything about how the system behaves. Rather than trapping gas and building pressure until it eventually bursts, this porous lid allows gas to escape slowly and continuously, venting upward through the very features that make Yellowstone famous: its geysers, hot springs, and fumaroles. Researchers have compared this process to slow, steady breathing, or to a self-sealing lid that periodically releases small belches of gas rather than holding everything in until the pressure becomes unbearable. This constant, gentle release is precisely what keeps underground pressure relatively stable instead of allowing it to climb toward the threshold needed for a major eruption. It doesn't mean the system is dead. The magma reservoir has existed in roughly its current form for around 2 million years and remains, in the words of the researchers, a lively and dynamic system, made up largely of rhyolite, the same explosive magma type responsible for Yellowstone's past super eruptions, combined with supercritical water. But right now that system is venting efficiently rather than storing energy. It is, as the researchers put it, a sleeping giant rather than an extinct one. And knowing precisely where that boundary sits and how it behaves gives scientists an entirely new baseline for identifying whether that balance ever begins to shift. The third development goes even deeper, addressing a mystery that has puzzled geologists for far longer than either of the other two studies. What actually powers Yellowstone in the first place? Most active volcanoes on Earth sit along the edges of tectonic plates, fed by magma generated where one plate grinds beneath another. Yellowstone sits nowhere near a plate boundary. It's planted firmly in the middle of the North American continent, which for decades led scientists to favor the idea of a mantle plume, a narrow column of unusually hot rock rising from deep within the Earth, almost like a blowtorch aimed upward from the planet's interior, independent of plate tectonics entirely. In April 2026, a team of researchers led by Zabin Kao, working with colleagues from the Chinese Academy of Sciences and collaborating institutions, published a study in the journal Science. Using a new geodynamic model built from reinterpreting decades of volcanic and seismic data, the team proposed that Yellowstone's magma doesn't come from a deep mantle plume at all. Instead, it originates from the shallow upper mantle, the asthenosphere, and is delivered through what researchers describe as a mantle wind, a broad, slow, horizontal flow of hot rock moving eastward beneath the North American continent. This mantle wind, according to the model, is generated by the long-term subduction of the Farallon Plate, an ancient tectonic plate that mostly disappeared beneath North America tens of millions of years ago but left deep remnants still influencing mantle flow today. As this buoyant material moves beneath the thick continental lithosphere, it gets pulled downward, and that stretching creates the right conditions for decompression melting, generating the magma that eventually feeds into Yellowstone's plumbing system from below. Rather than a chamber sitting in one static concentrated pool, the magma exists as a broad, diffuse mush spread through the lithosphere, tilting toward the southwest, with only occasional temporary pockets of liquid-rich magma forming closer to the surface before an eruption. This reshapes how scientists model eruption risk going forward, because it means the underlying engine driving Yellowstone's heat isn't a fixed plume locked in one place, but a dynamic system shaped by the slow churn of the mantle itself. One that, according to researchers involved, is also on a very long-term trajectory of burning through progressively colder, harder, and thicker crust to the northeast of the current caldera as the tectonic plate continues its slow drift over the underlying heat source. Put these three findings together, and you get the real reason people are calling this a new phase for Yellowstone, even though, as USGS scientists are quick to stress, there's no sign of an imminent eruption. It isn't that the volcano suddenly became more dangerous overnight. It's that scientists suddenly have dramatically more information than they did even 2 years ago. Information revealing a system that is more seismically active than previously documented, that manages its own internal pressure more effectively than once assumed, and that draws its fuel from a mechanism entirely different from what textbooks described for the better part of half a century. Each of these discoveries individually is reassuring in its own way. The gas-rich lid explains why pressure isn't building toward catastrophe. The AI-revealed earthquake swarms are attributed to shallow fluid movement, not deep magma ascent, and the mantle wind model gives scientists a coherent, physically grounded explanation for Yellowstone's behavior that didn't exist before. But together, they represent a genuine leap in understanding, the kind of leap that changes what scientists watch for, how they interpret unusual signals, and how confidently they can distinguish between normal background activity and something that would actually warrant concern. That distinction matters enormously because the type of hazard Yellowstone actually poses on any meaningful human timescale isn't a super eruption. It's hydrothermal explosions, exactly like the one that tore open new vents near Black Diamond Pool in June 2026. These events happen when shallow pockets of superheated water flash instantly into steam, blasting through rock, mud, and sediment with tremendous localized force. They're smaller than a volcanic eruption, but they're also far more frequent, far less predictable, and capable of happening with almost no warning. The June 2026 event, while dramatic, was actually smaller than a similar explosion that occurred in the very same area back in 2024, when a larger blast at Biscuit Basin sent debris flying and closed part of a boardwalk to visitors. Following the 2026 event, Yellowstone Volcano Observatory scientists installed temporary seismic monitoring stations directly in the basin to capture data on how these newly formed vents evolve, and researchers are now poring over the recorded signals looking for any precursors that might have hinted the explosion was coming, in hopes of someday being able to give visitors and park staff advance warning before the ground gives way beneath a popular trail. This is worth sitting with because it reframes what watching closely actually means when scientists say it about Yellowstone. It isn't code for expecting a super eruption. The USGS Yellowstone Volcano Observatory has maintained a normal alert level throughout all of this. The lowest of 4 alert tiers, the same status Yellowstone has held for years. Current estimates place the magma beneath the caldera at only somewhere between 5 and 15% molten, far below the threshold of roughly 50% needed before an eruption becomes physically possible. The annual probability of another super eruption is currently estimated at around 1 in 730,000, a number so small that, statistically, you're enormously more likely to be affected by countless other natural hazards in your lifetime. And crucially, if that probability ever did begin shifting, the monitoring network now in place, 46 seismometers, 26 continuous GPS stations, satellite deformation passes multiple times a day, and now these newly enhanced machine learning detection methods would be expected to pick up unmistakable precursor signals. Sustained earthquake swarms reaching magnitude 4 and above, persistent harmonic tremor, ground uplift measured in meters rather than centimeters, and significant shifts in volcanic gas chemistry. Scientists estimate that a genuine eruption sequence would unfold over weeks to months, not hours, giving authorities meaningful time to respond, long before anything approaching a crisis point. It's also worth putting Yellowstone in context against the rest of the world's supervolcanoes, because the comparison reveals something important about where real urgency currently lies. Yellowstone ranks among the most closely studied and heavily monitored volcanic systems on the planet, precisely because of its history and its popularity as a national park. But many volcanologists argue that the supervolcano deserving the most immediate concern right now isn't Yellowstone at all. It's Campi Flegrei, a vast volcanic caldera just west of Naples, Italy. Unlike Yellowstone's remote wilderness setting, roughly 500,000 people live directly inside the Campi Flegrei caldera, and the ground there has been steadily rising and falling for years, accompanied by increasingly frequent earthquake swarms. The contrast underscores an important point. Raw geological potential is only part of the hazard equation. Population density, monitoring infrastructure, government preparedness, and the specific behavior of each individual system all shape how much genuine risk a caldera poses at any given moment. Yellowstone's remoteness, combined with the sheer density of scientific instrumentation surrounding it, places it in a far more closely watched and better understood category than most of the other calderas capable of similarly enormous eruptions. None of this is to say that Yellowstone should be dismissed as harmless, or that scientific vigilance is misplaced. Quite the opposite. The reason we now know so much about the gas-rich cap, the mantle wind, and the 86,000 previously hidden earthquakes is precisely because researchers refuse to treat normal alert level as a reason to stop asking questions. Every one of these breakthroughs came from scientists pushing existing monitoring technology further, applying new tools like machine learning to decades-old data, and physically hauling 53,000-pound trucks into the backcountry to map structures nobody had successfully imaged before. That persistent curiosity is exactly what allows a park that welcomes millions of visitors every year to remain both open to the public and genuinely safe, even while sitting atop one of the most geologically significant features on the continent. So, when people say Yellowstone has entered a dangerous new phase, the most accurate way to understand that phrase isn't as a countdown to disaster. It's an acknowledgement that our picture of what's actually happening beneath the surface has changed dramatically in a very short window of time. We now know the caldera is more seismically restless than the official record ever showed, yet that restlessness is largely explained by shallow fluid movement rather than rising magma. We know the volcano has a natural pressure release mechanism operating just a few kilometers down, one that's been quietly doing its job for who knows how long before anyone actually found it. And we know, for the first time with real physical modeling behind it, roughly how and why this improbable continent-locked supervolcano gets fed in the first place. Each discovery closes one question and opens several new ones, which is exactly how scientific progress at a site like this is supposed to work. The Norris uplift anomaly rose and settled just as it has twice before. Biscuit Basin blew open new vents, just as it has done multiple times in recent years, and will likely do again. The earthquakes keep coming in their hundreds each month, mostly too small to feel, occasionally clustering into brief, unremarkable swarms. What's different now isn't the mountain, it's us, our instruments, our models, our capacity to listen more closely than we ever could before to a landscape that has been rumbling, venting, and slowly reshaping itself for millions of years, long before anyone was watching, and long after any of us will be around to see what it does next. Yellowstone just cracked open again, and scientists caught it on camera. At 5:09 in the morning on June 13th, 2026, monitors at Biscuit Basin picked up a burst of seismic energy and a low-frequency acoustic pulse. Within hours, the Firehole River turned milky gray for 3 miles downstream. Steam and rock blasted from the ground near Black Diamond Pool, carving 3 new vents into the earth. It wasn't the first time this exact spot has done this, and it won't be the last. Yellowstone isn't a mountain with a crater. It's a caldera, a collapsed basin 30 by 45 miles wide, formed after massive eruptions drained the magma chamber beneath it. That's happened at least twice in the last 1 million years, most recently around 631,000 years ago. Since then, Yellowstone has vented its energy differently through the geysers, hot springs, and mud pots that define the park today. Starting in July 2025, ground on the North Caldera Rim began rising, echoing a pattern seen in 1996 and 2004. By mid-January 2026, it stopped. Deformation has stayed flat since. Earthquake activity sits at background levels. But 3 scientific breakthroughs, all landing within about a year, changed what researchers actually understand about this system. First, machine learning applied to 15 years of seismic data revealed over 86,000 previously undetected earthquakes, 10 times more than known before, mostly small swarms driven by shallow fluid movement, not rising magma. Second, a nature study used a 53,000-pound vibroseus truck, and 600 sensors to locate a gas-rich lid 2, 4 miles underground that lets pressure vent slowly and steadily rather than build toward catastrophe. Third, a science study proposed Yellowstone isn't fed by a deep mantle plume at all, but by a shallow mantle wind of hot rock pushed east by the ancient subducted Farallon Plate. None of this means eruption risk increased. USGS still holds Yellowstone at normal alert, the lowest tier. The magma beneath is only 5 to 15% molten, far below the roughly 50% needed for eruption. The annual probability of a supereruption sits near 1 in 730,000. Scientists say any real precursor, magnitude 4+ swarms, meters of uplift, shifting gas chemistry, would give weeks to months of warning. The actual hazard on a human timescale isn't a supereruption. It's hydrothermal explosions like Biscuit Basins, sudden, localized, and hard to predict. That's exactly why scientists installed new monitors there after June 2026, hunting for the precursors that might one day warn visitors before the ground gives way. So Yellowstone hasn't become more dangerous. Our picture of it has become dramatically more detailed, and that's a very different thing. If you want more science broken down like this, subscribe, drop a comment on what to cover next, and share this with someone who thinks Yellowstone's about to blow tomorrow.